How are you? Doing good.
Good. Great to see you guys again.
Yeah, it's great to see you too. Thank you so much for hopping on call again
How
with
did
us.
we not see each other at comp? How did we
I
miss?
know.
I don't know how we did that. I know you guys, it's crazy and it's crazy for me too, nonstop, but for sure we should have at least crossed paths. So I apologize. Your message was sent on time. I just didn't check LinkedIn, I think, for like 4 days straight because it was just a chaos there in Michigan. But how did, real quick, how did it go for you guys?
So it's definitely the best we've done since probably 5 years.
Ah,
Um,
fantastic.
yeah, so I think you knew what we were last year or the year before this, upcoming year where we're at. Um, and we were second to last overall, but this year we were 22nd place overall. And then
Amazing.
we passed all technical inspection and we got to compete in all the dynamic events. So we're really happy
Amazing.
about it. Yeah.
And the competition every year is a little bit better than the year
Yes.
before.
Yeah.
So that's a huge accomplishment. Congratulations. That's amazing.
Yeah. A lot of it is thanks to your help. So
Well, listen, guidance is easy, doing the work, actually building and testing and wrenching and then preparing and then going and executing. That's all you guys. So good stuff.
yeah. All right. Well, I don't think you've met Nan, Gian, and Adrian yet, but they're going to be our this year's Aero and kind of composites leads. And so they prepared like a couple of things they want to show you of like what their plans for this upcoming year. I think you know that the last year we didn't run any aerodynamic or we didn't run an aero package at all. So we're kind of just focusing on like learning and get that in. So this year we really want to implement it. So this is their
Awesome.
plan. Yeah.
Awesome.
I'll hand it over to them. But yeah,
Yeah.
they have a couple slides for you.
Yeah, I'll get started. Yeah, thanks for the introduction. Yeah, again, we're the Aero leads at Formula Racing UC Davis, and today we'll just be going over our kind of preliminary design for this year and looking for some review with you, Jim.
Awesome.
And yeah, let's get started. So, again, yeah, big thank you, Jim, just coming out and taking time out of your day for this and also rescheduling. That was great. We're really excited and thankful for your help in this.
All good.
But yeah, so my name is Adrian. I'm a third year mechanical and aerospace engineering major at UC Davis, and I'll be the composites lead.
I'm Nan. I'm a third year mechanical engineering major, and I'll be this year's aerodynamics lead.
Oh, I'm not getting audio.
Oh, can you hear us?
Is this it? Okay.
Yep.
Let me just. Okay. Uh, all right. I'm a my name is Jian Ha. I'm also a third year mechanical engineer. And I'm also the Aero co-lead. Yes.
kind of an overview of what we are going to be talking about today is our package goals and also our design concept. Following with angle of attack design study configurations, as well as validating that with CFD results and aero balance. And generally, we want to talk about the aero performance impacts on the car, and then manufacturability, and then as well as improvements. So this is our design concept for this year. We try to push for a rear wing and front wing and also an under tray. As of right now, the under tray is kind of being pushed back a little bit since it's heavily relied on the chassis um, configuration. So we wanted to focus more on the front wing and rear wing because of more um, design space. Next slide. Some aero package goals, like I mentioned, we're pushing for a front and rear wing and under tray. Some weight goals that we have in mind is front wing being 10 pounds, rear wing being 15, and under tray being 20. These are generally overestimates, we feel like, so it could vary on the weight goals. Um, as well as balance goals, we want to push the center of pressure as much as close as possible to the center of gravity because of the balance setup that we had. We previously talked to suspensions and the driver, and their feedback was they want it's a little bit understeer, but there's a lot of like room for improvement as suspension side to help with that. So they want to opt in for a more balanced setup on our end. Some performance goals. We ran a lap sim data or lap sim simulation. Currently, our lap time is around 57 seconds. So generally, we want to shave at least 3 seconds off the lap time with Aero. So our target region for coefficient lift and coefficient drag is 1.4 to 2.2, and as well as 0.3 to 1.2.
Yeah.
And Gian will talk about the front and rear design.
Yeah, so this is our the current concept for our front and rear wing. An issue that we initially had, because our initial design had 3 elements for both our front wing and rear wing, but we had some issues with our center of pressure being too far forward, and so we decided that like switching up the elements would help change the balance and bring it back and also make a less aggressive airfoil setup. But yeah, so our front wing has 2 elements and a curved, like it's curved on the end plate for the trailing edge. Yeah, to ensure that airflow goes around our tires instead of hitting it. And then for the rear wing, it's 4 elements, and in 2 slides, it'll explain why I chose that specific airfoil configuration. And then the notch on the top trailing end corner is to reduce the vortex that forms off the edge, going of like the high pressure air spilling over on the outside of the end plate. And yeah. And for Nan, do you want to explain the under tray?
Yeah, so for a general under tray design that we have in mind is having key features of a rear diffuser as well as internally inlets and outlets. The side outlets is kind of like a best of both worlds to help with our side radiator cooling as well as improving our downforce.
Yeah, and so these are the airfoil configurations that I had tested in 2D sims. It shows the main element angle of attack, its position, and then the second element for the front wing because there's only 2. And for the rear wing, there are 4. Yeah, and it's just like the basic data that we use to help us point us into the right direction for what setup that we want to use. And this is the actual airflow of the rear wing. And we found, okay, so we wanted to have like at least like at most just 2 different chord lengths for composite sake to make it easier to like be made, and so we don't have to make so many molds and like spend weeks and weeks. So we decided that if we want to use multi-elements, we would use the same chord length for the secondary, third, and fourth. And so we went with 300 millimeters for the main, and then with like -1 degrees angle of attack. And then second element is 150 with 35. Third is 150 with 55, and fourth is 150 with 25. And the reason why the fourth element is under all of the other elements is because I did see a couple of like pictures that Adrian sent me from competitions like with other teams that have another element on top. But when I did the 2D simulation, there was just a lot of turbulence and like there was no setup that I could do where like it wasn't separating and detaching. And so my theory with this is that like like having an element under the main wing around that area will help speed up the flow and avoid separation from the upper elements. Yep. And then this is the front wing airfoil 2D simulations. Uh, we also wanted to keep it at 300 and also 150 millimeters. And we found -1 degrees, and we went with two different setups, and we're planning on making it adjustable and possibly like a third one, but we still need to like do further research for that. But one really big flaw that I realized last night when I was making these slides was that the 2D simulation was made ignoring the ride height. And so, yeah, in the future, uh, I should probably change the domain in order to properly get the accurate data. Yeah. And this is just the airflow of both of the different configurations with the full simulation. I mean, full simulation body. And if you can see on the right hand pictures for the top and bottom, the front wing, the airflow looks completely different from what it was in the last slide. So that just confirms my mistake there. Yeah. Also another like design parameter was the height of the rear wing. We just wanted to like bring it as low as possible without obstructing the flow that the rear wing gets. And we found this is probably around the lowest that we can go. But yeah. So these are our CFD numbers. Our the yeah. So the first coefficient, the first setup, the CD is 1.3, the second setup is 1.39, and so forth. The the first setup is a little bit less downforce, but the benefits of that is having the center of pressure closer to the center of gravity. So it'll have a little bit of stability. But the drag range is looking around like 17.81 pound-feet to 18.32 pound-feet, and for drag is 3.877 and maximum 4.296. And obviously this is a huge gain like compared to no aero, since we're making lift with no aero just for the chassis setup that we had to accommodate for the full package. Yep. And so this is showing the graphics of the center of pressure and how it changes with our configuration. And we don't have an exact like number for a center of gravity, so we're just putting a placeholder at like a quarter of the like distance between the wheelbase from the rear, just accommodating for the accumulator, the motor, and the actual driver, since they'll all be like near the back. And so as you can see, the first configuration just is a little bit closer to the center of gravity, which should give us a little bit more stability. And I'll give it to Man here.
For aero impact, like Gian mentioned, with no aero configuration, our we're producing lift without any aero at around 25 miles per hour. Like I mentioned earlier, the lap time is around 56 with the aero efficiency of 1.2. With the full package and the configuration and the weight included, our lap times reduced by about 3 seconds, which is our overall goal, as well as our efficiency increased by 86%. Also, since the CL and CD targets are met, there's obviously a region of lift to drag ratio that we could further reduce the lap times in that region. This is our lateral and longitudinal acceleration impact. Obviously, you can see that there's a 30 to 50% gain with having aero and having no aero. And Adrian will instruct the.
All right. Yeah, I'll be discussing a little on the manufacturing of our aero package. It's not worth much if you can't make it. So for our front wing, we want to use a shell design with a ribbon spar structure. This means that we'll lay out the carbon fiber on a female mold, which will give us a shell to attach onto our ribbon spar structure. So the internal ribs will be laser cut wood attached onto an ideally carbon fiber spar. We'll have end caps with 3D printed end caps with heat set inserts, so we can fasten them onto the end plate. And there will also be a mounting rib in the middle of the element. So that element will be mounted onto a mounting bracket, which will connect onto the two blue ribs. The photo you see in the picture is the main element. The secondary smaller element will be pretty similar, but instead have one spar and no mounting ribs. We chose this because of our kind of experience and the access to what tools we have. In our campus, we have a large laser cutter, a router we're familiar with, and a new water jet in our machine shop. So we want to make use of what we can. If we had like a CNC foam cutter, we could kind of go into that a wire, like potentially wired foam cut inner airfoil and then lay up carbon fiber on that. But for now, this is what we can do and what we're pretty familiar with. Again, since we wanted to simplify our design, we have 2 airfoil profiles, which mean we'll have only 2 molds that we need to make. And each mold will have 2 halves. So, essentially it's 2 airfoils and 2 molds per airfoil. So 4 molds in total. We'll make the molds as large as we can and lay it based on the length we need, which is mostly determined by our track width. And the largest mold we can do on our router is around 4 feet, but our front wing spans about 5.5 feet. So we will need to split that front wing in half, but ideally the rear wing should still be in one piece. These will be machined on high density foam, and we'll experiment with both wet and dry layups, see which one we like more, which one is easier, as we'll be making a lot of these different elements. For our end plates, we had some experimentation last year with how we wanted to go about making them. For what you see in the picture, what we did was we laser cut a wooden frame. We filled it with honeycomb, and we applied prepreg on the top and the bottom. So this was pretty ideal for us, as we could prevent compression on the carbon fiber, as we saw that was an issue when you fasten onto it. It could start to compress and maybe debond. This also allowed us to locate our mounting holes, and it gave us a pretty nice outer edge to hide that honeycomb and also give us a surface to put weather stripping on. Since this is a slightly smaller test, we aren't really sure how big or how good it would do with larger end plates. But for now, this is what we seem to like and what we'll probably go with. And for our under tray, again, we haven't really gotten that design nailed down, but I found a video by UG Racing on YouTube, and I think this is pretty similar to what we want to go with. We want to do a male mold and lay up our ideally pre-preg carbon fiber with a honeycomb core, for our stiffness. And hopefully we can do it in one piece. If not, where we might split it into three, where we have two on the sides and one piece for the diffuser. Again, the under tray is pretty dependent on our chassis, so we haven't, designed too much, or we haven't looked too much into design for that. But as our chassis gets finalized, we're able to figure out those mounting points and figure out where we can place our wings. And here's a small timeline for how we want to go about this. So from now up until around the second week of fall quarter, we'll start making our test pieces and our molds. Again, since our airfoils are mostly dependent just on our cord length and our span, we're able to get a head start on making those molds in fall quarter. So around the first month of fall quarter, we'll start making the molds. And hopefully by around the middle of fall quarter, we can start laying those shells up. Once we have those shells done, we can start manufacturing the end plates and the ribs, which again are 3D printed and laser cut respectively. And finally, we can hopefully water jet our brackets out of aluminum. And we'll spend our winter break catching up if needed. Then once our chassis is finalized, we can design our mounting brackets for the proper loads and location, and hopefully manufacture those around the start of winter quarter, where then we can also assemble our front and rear wing. Then we'll take about a month manufacturing the molds for the nose cone and the front panel and lay them up for the next 2 weeks respectively. And hopefully we have our main aero components installed on the car by the end of winter quarter. Then as those are going on, ideally once we get chassis finalized, then we'll start our under tray design and optimization. And hopefully starting spring quarter or end of winter quarter, we'll start the mold manufacturing for our under tray and lay that up. And hopefully by the middle of spring quarter, we'll have everything done and can focus on testing. And yeah, that's all from me. Again, yeah, this is just a kind of preliminary design, but just wanted to see if you have any comments, questions, or feedback.
I took 20 notes. Most of them are questions. Okay, so I'll start with the second half, Adrian. So as far as manufacturing goes, I think you did a great job of explaining what you did and why you did it. Okay, I will get to the design and analysis and to I'm sorry, is it Gian?
Yeah,
okay. Yeah, okay. So I'll get to Non and Gian second, but I'm going to start with Adrian here. Great job of explaining what you did and why. I'm leading, by the way, into the second half, right? What's your plan of attack for different ply counts? You mentioned that, I think it was the next slide or the slide after, you were like, yeah, right here. You're going to play around and experiment. Experimentation takes time and resources and money and effort, all right? So if you can reduce the amount of what if scenarios, right, you can get it done quicker. So can you logically predict which one would be better, faster, smarter, whatever? And that's with the process, wet versus pre-preg, right? Different ply count. That's a manufacturing aside for a second, that is a stiffness, strength, and weight optimization problem. So what are you thinking there?
Yeah, so we kind of base it off of our ply count for our front panel and our nose cone this year. That for this year we used 3 plies. We did a wet layup, and we were kind of happy with how stiff it was, especially for the front panel. Just a large square structure. We found it to be pretty stiff. So ideally around 3 plies, but we wanted to do the testing especially with the pre-preg to see if we can get away with 2. See how stiff that would be. Again, they would be kind of orientated at 0 degrees and 45 for that, for more stiffness. But I think if we wanted to just kind of overshoot, we do 3 plies and wet layup, which we think is the stiffest.
Yeah, I mean, there's some simple hand calcs, right? Simple beam, you know, a wing is just a beam, or a beam is just, you know, you're literally just simply supported on both ends. For the rear, or however you're doing your mounting structure. Maybe you have a mounting structure in the front, in which case it's symmetrically, you know, simply supported. There's really, really simple hand calcs that will help you just distill down to general order of magnitude. And you can do some simple hand, it's like linear math, right? Simple fundamental, like just composite theory, right? And just say, okay, if I've got this layup, it's this, you know, this combination of elastic modulus and a bulk modulus. What's the stiffness of the structure, et cetera, et cetera. So that's a simple like stiffness sort of strength. You know, you can just, you know, where's the max stress and can we handle it, right? And put some factor of safety on it. And you can easily calculate like a, you know, I got a, you know, whether it's a, is it a foam core or is it hollow? I missed that.
Should be hollow.
Hollow, yeah. So you can easily just calculate like a corresponding area and cross-sectional area. So simple beam math, statics 101, you know, just sort of a composite structure, just to get a ballpark. Otherwise, you know, with composites, nothing beats a quick and easy, dirty test. And I've actually seen a team do a quick layup, like fasten it to the side of the bench and hang weights off it. And I know you're laughing, thinking like, well, what does that mean? Like literally, like that's engineering. That's what we do in the garage. That's when we go racing. Like, and we want to know what's happening. And I don't want to, you know, make a perfect mold, go to an Instron machine, you know, or use a third-party test house. All those extra money and time, like just literally like hang weights off and see what happens. And something as simple. And I saw that in the competition this past year. And I asked them. I said, how did you fasten it to the bench? How did you decide which weight to apply? They had great answers for both. And I said, that's an awesome test. You know, it's a really, just to give you the confidence of 3 versus 6 versus whatever, right? Because at the end of the day, what you guys are trying to do is minimize the amount of mass that's being added. And particularly with the rear wing, you're adding mass above the CG. You're raising the CG. You have literally just raised the CG. Your suspension team hates that. But what you're doing with your lap time sim is saying, listen, I know we take a hit on weight, we take a hit on CG height, but the gain of the downforce, and we take a hit on drag, right? Because we're increasing the cross-sectional area, the frontal area, but the gain from the downforce in the, say, medium and fast speed turns is a reduction in three seconds per lap. So suck it up. So, you know, that's the story that you guys need to bring, right? And from a stiffness and strength standpoint, you're in control, Adrian, of how much weight really is being added. As far as the layout of this, the way that you've got it hollow and with the spars and the cross beams, I think that can be definitely a winning recipe. Just got to get a little more handle on, you know, the epoxy. You screw the epoxy up and the thing's gonna come out 10 pounds. So just little things like that. I think if you got a handle on that, you're in a good spot. And another thing you mentioned was your end plate design. You've got that like kind of CNC wood kind of frame, and you've got the honeycomb that sits in between. You get this. We'll look into other methods. Don't. That looks great. If it works and you've created basically a solid puck or an insert, so you can compress and get your torque on the bolts without crushing the stop. Don't even look at any other method. You've got a good one. Move on. You know what I mean? Like, listen, after you build it and you weigh it, and install it and go run and test. If you've got some feedback for yourself for next year, that's fine. But right now, I don't see any issues why you would try to invest any more time in any other method. I don't see anything wrong here. So, okay, that's it on the manufacturing side of things. The other 17 points of notes that I made, guys, are for the design and analysis side. So let's go all the way back to the beginning. Okay. Let's go to the next slide. At first, I wasn't putting slide numbers in, so I'm sorry. Yeah, go to the, okay, right here. Weight goals. Where do these come from? 10,
These came
15,
from
20?
These came from me. At comp this year, I was asking a lot of different teams, like what their weight goals or how heavy their aero packages were. These were kind of the upper end of what I heard from teams. And I kind of wanted to set this as a target for us to beat, which should be pretty easy. You know, I know a 10-pound front wing can be a lot, but one of our older alumni, you know, tried making a front wing, and it was also around 10 pounds. So we wanted to, set that as our upper limit and try and shave weight from there.
If this is going to be your story, if this is part, like if this presentation is part of the story you're bringing to the design part of the competition, make sure you're ready to tell that half. Because whenever I see a goal, I always ask why, or where did that come from? And weight goals in particular, especially with a team first year Aero, I know you don't have years and years of historical data of manufacturing methods. So I'm already thinking to myself, like, where do these numbers come from? Research is okay. Engineering, when we're doing stuff for the first time, we only have research, right? We don't have data. So going around and asking teams, I think, is okay. As long as you do many teams, and to your point, you're conservative with your with the numbers there. And then I think I'd like to also see, or as I have, if I have my design judge hat on, I'd like to also see, by the way, we just told the team that we're going to add 45 pounds to the car. My next question is, did you add 45 pounds to the car in your lap sim?
Yes.
You did?
Yeah.
Highlight that, because I didn't see that in the slides. I only saw like with and without Aero. And that's actually something that teams accidentally forget. And what happens is, and it could be an accident, sure, but what happens is you get this overestimate of the impact of the Aero. And that is dangerous, right? That's very dangerous, because then we're really excited, and then we go out there and the car's slower. So make sure you highlight that. Like, hey, like our weight goals are adding 45 pounds. We know that we're going to be adding X amount of predicted downforce with minimizing drag. And as a result, we have a 3-second lap timing, improvement. So, okay. That's all good. Balance goals, aligning the center of pressure and the center of gravity as much as possible for a balanced setup. Okay. You're missing some information there. Okay. And this is just fundamentals 101. The center of pressure is a function of what?
Time. Right?
What?
Function of time?
It is, but what's the key input of what's changing every lap as a function of time? Yes, yes. Your balance goal needs to include a center of pressure either at a velocity or what we call center of pressure migration. Saying this center, our ideal center of pressure is at, say, the average lap time, or the average lap speed, excuse me, which is just a lap, which is just the total time, right? Divided by the distance, distance over time. And so you can get your average velocity, right? Let's say it's 25 miles an hour. Okay. That needs to be on this slide, right? Our package goal has an assumption, and that assumption is the nominal velocity that we're targeting is the average speed of a lap of 25 miles an hour. That's your starting point. Now, I can pick a hole in that logic, but at least it's a starting point, right? Because the average speed of the lap isn't necessarily the speed that's going to impact your lap time. It's the faster speeds. It's the medium and high speed turns that when you gain downforce, you are going that much faster. So, but I don't want to flood you guys with too much information right now. All you want to do is document all of these assumptions, because a missing assumption, you're going to get picked apart in design, which, okay, fine, might be worth a couple points, but a missed assumption could steer you guys in the totally wrong direction. And that's going to hurt in the dynamic events, which is the most fun. So in the balance goal, you have to have on this slide, like, okay, we're targeting general center pressure, sort of our balance at 25 miles an hour, and the location of that center of pressure at 25 miles an hour, we want to be, according to you, aligned with their center of gravity. What that means, right, is that as the car, if you were to compare the car at a low speed where you have very little aerodynamic help, very low forces, then you're going to design a suspension and a car to have, say, a balance. You say balance setup. What does that mean? No oversteer, no understeer, right? And a balance setup would be, what the driver wants versus what you guys think is the fastest setup, okay? What you also want to know is, as you get up to your 25 miles an hour, and then you're 30, and you're 35, and you're 40, and your max, which is probably what, 50 on endurance, right? 55? Do you have data on that?
We don't. I don't have it on hand right now. No. Yeah.
Okay, that's got to be on here too. Like, you should have absolutely on the first couple slides The aero team needs to know what's our average speed, what's our max speed, because it's so important. Everything's a function of velocity. I don't even know if I saw the word velocity or I saw a velocity anywhere in the design and analysis slide deck. So that's got to change, right? So once you come out and say, all right, Jim, our average speed is 25 miles an hour, our max speed is 60, I'm making numbers up. Then you say, okay, we expect the COP to be on top of the center of gravity, right at 25 miles an hour. Okay, what happens to the CP as you go from 25 up to 60? Because I'll tell you right now, if it goes in front of the center of gravity, you have a very dangerous but fun car to drive. Because what's going to happen is the rear wheels, as you start driving faster, imagine just doing a turn that, you're doing in that turn, you can max out that turn. Say it's a gigantic skid pad that you can go 60 miles an hour at. If you're going around that turn at 25 miles an hour, you have a balanced car. As you go faster, you have basically an oversteering car. Where's the power being applied? Where do you guys have? What is it, a rear wheel drive or all wheel drive, front wheel drive?
I think rear wheel drive.
Yeah, it's rear wheel. So MRX 228.
So, and it's, what is it? Driving a rear diff and driving a whole
it's Drexler
rear axle.
LSD.
So as you guys go from 25 to 60 miles an hour, you're getting more and more grip on the front and less increase in grip on the rear. Because if your center of pressure is moving forward, which I think is what you started to show us, is your center of pressure is forward of your CG. I have a lot of questions around the CG location, which sounds like you guys don't know where it is yet. But as the center pressure goes in front of the CG, that's drifting. Like this is not a drift competition. It'd be cool if it was, but at the end of the day, the rear end's going to start to step out as the driver tries to go faster, because the aerodynamic force on the front wing, which you have ground effect, which I don't think I saw those words anywhere in your design and analysis slides. You need to be talking about ground effect. Ground effect is a key phenomena that you guys are taking advantage of. You had mentioned it, I think, Gian, I think you mentioned it in one of the 2D CFDs, or maybe it was I'm sorry, like you had a 2D CFD that didn't have the ground.
Yeah.
Oops. Definitely a big oops, right? But what it's telling the audience is you didn't even factor in this phenomenon called ground effect, which is always there and becomes an increasing source of downforce. Okay. So talk about ground effect, talk about how you're taking advantage of it. And the front wing almost always is going to create more downforce, all things equal, right? That's what we have to fight against. It's got fresh, clean air. There's no blockage, there's no helmet, there's no gigantic head sitting in front of it like there is in the rear wing, right? And there's no roll cage, there's no other things, mounting hardware and everything that are making this dirty air hit the rear wing. It's a nice clean front air, and you get ground effect. So it is common to see the CP move forward as the velocity goes up. We have to fight that. Our job is to try to minimize that as much as possible. If you can't, then we just have to start with the CP being behind the CG. And then as speed escalates, the CP moves forward because that's physics, but it never gets in front of the CG. So your balance goal of trying to align the CP and the CG is, I think it has merit, right? Because you're basically saying, hey, as this car goes faster, we don't want the balance to change. We want the balance to stay even, and we want it to, continue to stay even so that the driver can drive it predictably. The problem with putting the CP on top of the CG is if your CFD is wrong, and most all CFD is wrong, and you're not really comfortable with where the CG is, if your CP moves from in front of the CG to behind the CG, or from behind the CG to in front of the CG, which can easily happen if it's close to the CG, because the CP will always be moving as a function of velocity. If it all of a sudden moves in front or moves behind, that's going to change the balance of the car. Does that make sense? Hard to drive. So just understand that the CP is always going to be doing this as you drive the car faster, slower, and around turns. Then you want to put it in a location where it never crosses over the CG. And generally speaking, we want it behind the CG in a rear-wheel drive car, because when you're coming out of a mid-speed turn and I'm a driver and I want to put that gas pedal down, not only is the inertia going to move the mechanical force to the back, But as I elevate my velocity, I'm going to continue to get more vertical force on the rear wheel. That just means plow it. Come out of that turn, full throttle, and plow it, and you know that the car is going to be nice and settled, as opposed to plowing it and all of a sudden you get lift in the back, which would be very dangerous but fun. Does that make sense? So I don't think this is going to require a massive design change per se, because you could probably just tweak a little bit of an angle of attack, which is an easy change to make in July, right? It's really easy to make angle of attack changes. Let's say, even if you decided on your airfoil profiles, you can just play with angles of attack and change that balance pretty easily. But I think you need to reassess your goal of putting the CP on top of the CG, especially since in a couple slides, you didn't know where the CG was. That's a problem. That right there is a problem. And you can, I know, like, is the CAD like 75% complete, or what? Why don't you know where the CG is? That to me is I got a huge question mark on that.
Okay, so we do have the CG from last year, but like the chassis that we're designing on now is like pretty different. Like the geometry is like really different as well, and like we just don't have the numbers because like the CAD that we worked on as well was only like the space frame chassis. It didn't include like a accumulator and its weight and the driver or
Yeah.
like anything else. Yeah.
Yeah. Forget the CAD. Just
Oh.
throw CAD. If the CAD isn't like 80 or 90% complete, then it's not a helpful tool in telling you where the CG is. Really easy Excel math can help you. Okay. So what's the total weight of the vehicle from last year, or roughly last year, this year?
640 pounds.
Total weight of the vehicle?
It's like around 280 kg. So
280 kg. Okay. Yeah. And that's no driver with no, that's no driver. No driver. Okay. So you got 280 kg. Okay. You got a driver that's going to weigh somewhere around what? 75? You know, maybe between, I don't know how small the driver is, right? 50 to 75 kg. So think about it like this. You know where the CG is of your frame or your total vehicle. Okay. Now look at the largest sources of that weight. You got a driver, which wasn't in that number. You got your accumulator, which is just a big hunk of solid mass. And that's located somewhere. You just go down to last year's car, okay, with a tape measure, okay, and say, oh, and then draw it out on a chalkboard or on screen or something and say inside view. Okay, inside view. Here's the wheelbase, right? Here's the CG. It's some percentage between the wheelbase. Okay. And what comprises the location of that CG, just look for the top 75% of that mass. You get the frame, you get the accumulator, you got your motors and the whole rear end. Just package it up and say, how much does it weigh? 10, 15, 20 pounds. Okay. Where's the center of the accumulator container? Or the accumulator container is heavier than that, right? But where's the center of the driver? Okay. Where's the center of the accumulator container? Okay. Where's the center of all the metal and stuff in the back? That's part of the drivetrain. Okay. Where's the other stuff that we didn't include? Maybe some electronics in the dashboard, maybe some other things, right? Now you can easily just do a weighted, weighted location, right? You ever done a quick like CG, like this percentage of the CG is here, this percentage of it is being contributed by this part, and that part is this location. So this subsystem CG is here, the subsystem CG is here, the subsystem CG is here, and you just do 3x diagram. Okay. Now, what did you change to this year? It doesn't matter that the geometry of the frame is different. Who cares, right? If you can estimate the frame to be about the same size, did the driver move? Because they're heavy. Did the accumulator move? Okay. Did the high voltage system, did the powertrain move? Okay. I'm adding Aero and their respective centers of gravity. And you can just estimate within probably 10 or 15 or 20% where the new CG is going to be. Does that make sense?
Yeah.
If you don't move the heavy stuff, then your CG is going to be pretty close to last year. So use that data and then because just guessing it being a quarter of the way up from the rear wheel is like, unless you back that up with a little bit of information, I don't have the confidence that's where it is. Now, once you figure out where the CG is, then go back and revisit the CP. Okay. Because if your CP is ahead of your CG, it's going to be a hard car to drive, number one. And I'm talking about at your 25 miles an hour, average speed. And it's probably going to go up as velocity goes up, because as velocity goes up, the effect of ground effect goes up. So the low pressure side of the front wing will go up. So you get more suction, if you will. You're certainly going to get more suction from the under tray if you end up putting it on. And the impact of the downforce, as long as you don't, separate the element, the impact of the downforce goes up as a V squared, guys, right? Dynamic pressure, 1/2 rho V squared. So every time the velocity goes up, you square that in force. So if you double the velocity from 25 to 50, guess what? You just quadrupled the downforce. So if you're already creating more downforce in front, i.e. your center of pressure is closer to the front than it is the rear, then the faster you go, it's only going to move forward. That's why we say you're almost always just going to move the CP forward as you go faster, because all of the effects of the downforce creating phenomena go up at a second order. So if what we're talking about today does prompt you, hopefully it prompts you to go back and do some fundamental math and just get better understanding of where CG is and where you want the CP. If you have to make a design change, you can easily do that by removing one of the elements in the front wing or changing some angles of attack, right? It can slide behind pretty quickly. So I think your CG is hopefully your CG is forward than where you think it is. And then you're able to get the CP a little bit behind. And then, you should at least have an estimation of where the CP is on average and where the CP would be at max, just so you can understand where its range of motion is. Just so that you guys can build the confidence that the phenomena is real, that CP moves as a function of velocity. And unless this is so well designed that it doesn't move, right? Like, just think about how many CFD sims and 3Ds and yaws and angles of attack and all kinds of ride heights, which, is not in your model quite yet. All of those things have to be accounted for. So obviously it's not something you're going to do this year, or maybe not even for the next few years, because it's so much sim work. But hopefully that gives you an idea of how much sim work some of the pro teams do. And when I say pro, I mean outside of Formula, right? SAE, but like some of the motorsports teams. And we are seeing some of that at the top tier in Formula. Not saying that's your goal, just so that you understand the level of engineering that is happening. So maybe that is a goal for you guys someday. So does that make sense, at least around the conversation around CG and CP? Okay, cool. Because that covers a handful of some of the comments I had about that. Which was basically, the number of aero elements and understanding how much downforce you wanted. What I always tell teams, which I don't see enough, is inside view. I would love to see a free body diagram. And that free body diagram is going to say, I've got my center of gravity with some level of confidence and the reaction forces on the wheels, right? And I have my center of pressure of the front wing and its location, the center of pressure of the rear wing and its location, and the center of pressure of the diffuser tray, etc., and where that is. And it's literally 1, 2, 3 points that represent your 3 aero elements, and 1 point that represents your center of gravity. That simple picture and that simple free body diagram for both downforce and drag is such an important way to communicate how you approach, what do I expect for performance in the front wing? What do I expect for performance in the rear wing? And those things will guide you. How many elements in the front wing? How much downforce do we need to get? How many elements in the back and downforce? Because every time you add an element, you add mass, right? Adrian's got to justify that. He's got to build these things. He's going to add mass to the vehicle. And again, in the rear, right? It's above the CG. So you're raising the CG. Particularly with the fourth element that's below the other elements in the rear wing, I want to challenge that a lot, just because of how dirty that air is. So you're gonna have to show me some good test data right? Which is expensive and hard to get with aerodynamics, right? With some good test data that the flow that is underneath the rear wing is what you say it is. That's probably the hardest part of the car to understand what the flow is doing, is behind the driver and beneath the rear wing. It is a hot mess back there. Absolute chaotic, turbulent. It's slow, it's messy, it's transient. It's not an area that you can really take advantage of unless your main goal is to take that weird, low pressure, chaotic, turbulent air and make it a little bit more laminar, smooth, pointed in a certain direction, and then you can put an element in there and take advantage of that. But if you're talking about messy, crazy air back there, it's really hard to extract forces, consistent forces, downforce, lift, So and that's my gut. Again, like we don't have enough data to justify that, but that's my gut. I'm like, you got to justify the extra beam down there. You really got to prove to me that that's really working. And so what you could do is have it in the design. Your hypothesis is it's adding value, but make it easy to remove. If you are like, you know what, it's not really doing much for us, just yank it out of there. Just take the weight off the car. Because anytime you can say, hey, the aero's not working for us. If we take it off, then at least we're making the car lighter. You're gonna get a high five from the judges, because we just want the cars to be light. F equals MA everywhere on track. Does that make sense? Okay. Angle of attack slide. Let's get some pictures. Yeah, if there's a way to communicate, we go back one. If we, like, there's like sort of matrix of different ways of doing angle of attack. I think it was, something like this. Just, I'm having a tough time just absorbing this information. It doesn't have any context for me, excuse me. So I think if there's a better way to just, you can have we like tables, because tables are a nice way in engineering to show data, but have some sort of pictures in here or something like that, just so I can understand what your sweep was and why. Like, I see 0 to 30 on your winglet, but which winglet, where on the vehicle is it? So just a picture, just to give me some context. That makes sense. It's just sort of like engineering sort of communication. All right, before you start showing any CFD, you got to explain to the CFD setup, right? So you got to explain, like, hey, this is our CFD model. And to your point, it was like, okay, here's the inlet velocity. What is it and why? Here's the, here's the turbulence model that we used, and here's why. And then, 2D models are good for just getting general understanding, for beams and slot gaps, but you can't get forces. You can't get really accurate forces. You can't really get real accurate turbulence out of a 2D model. So, just if you're doing 2D, that's totally fine, but just make sure that, like, you understand that it's a limited accuracy level, just because the real world's 3D. And in particular with fluids, turbulence is a 3D thing. There's no such thing as 2D turbulence. Vortices don't care. Vortices are just going to do their thing in all 3 dimensions. So as soon as you do a 2D sim, you can get some information. There's a way for us to mathematically account for turbulence, but there's going to be an automatic error in there. Just recognize that, have ready to talk about it. Because if you show a 2D sim to an aero judge, they're gonna be like, what did you do? Why did you do this? And it's okay to say, listen, our hardware and computing resources are not high enough for us to be doing 3D sims all day, every day, 24/7. And we're realistic in what information we're getting from a 2D sim, which is understanding general proximity, like slot gap, and general angle of attack. I don't think anyone's gonna say anything negative about that. So yeah, like I said, you gotta be able to explain ground effect, what it is, why. Basically we've got an aerofoil, right? And in an airfoil and free stream, you've got a certain amount of acceleration, right? Like you're showing right now, right? You've got a certain amount of flow acceleration. And as the velocity goes up, the pressure goes down, right? That's how it works. And so as we accelerate the air underneath, in this case, in free stream, your acceleration is only due to the longer longer path it has to take, right? The shape, if you will, or the camber, if you will, of this profile. So ideally, more camber, more Bernoulli effect, if you will, or more sort of acceleration we get of the air. As soon as you put a wall near that, i.e. the ground, now you've got a nozzle. Because you're not just accelerating the air around it, but you've constrained it with a wall. The air is going to accelerate more. So this effect that we get of a low pressure sucking you down and a high pressure pushing you down, and the high pressure comes from the angle of attack. So in your front wing, right, you're predicting a certain amount of downforce. You're actually under predicting downforce because you're going to get more downforce in the proximity of ground because you're going to get more acceleration, right? The air isn't going to be able to kind of go around like this. It's just going to get squeezed into that little nozzle and then go out behind. So you're under predicting downforce when you don't include the ground. So if you don't have any more sims to run and you're going to go to production with this, mention that to the audience. Hey, so by the way, we're new in CFD. We are familiar with ground effect. We just didn't have the setup. Just again, you just want to explain that you understand the phenomena, whether or not it's been included in the model or not. I think that just being candid and open and transparent is very, very helpful in understanding where the sources of error is for CFD. So, so got to talk about ground effect and taking advantage of it. And generally speaking, if I've got three choices of adding, I'll just say adding weight to the car, a front wing, a rear wing, and diffuser. Generally speaking, the front wing, if I were to rank them in how much drag I'm adding, number one, the rear wing, right? You just added this billboard, you look at the vehicle and the vehicle just got twice as tall, So the frontal area of the vehicle goes up a lot with the rear wing. So you're adding drag, right? You are adding a little bit of drag with the front wing. Now, granted, you look at the car in the front area might change just a little bit, right, with the front wing, but you can't go wider than the wheels. So it's not like your front wing isn't going to block the view of the driver, right? So you're not really adding any frontal area, but you are, there's air that would be going, say, through the suspension or around the tires, and you have blocked that with a front wing. So the front wing adds a little bit of drag. That is because both of those have angles of attack. And so you're putting a wall up, right? If the angle of attack was 0 and there's no camber on it, you're really not adding much of a cross-sectional area, which is where a lot of drag comes from. As you add the angle of attack in the second, third, and fourth element, you're starting to slow the car down, really, because you're adding this wall. The diffuser adds very little, if any, drag, because it's only creating downforce due to ground effect. It's only creating downforce due to an acceleration of air in the front half of the floor, if you can design it right, and then the expansion of the air in the diffuser. So the whole purpose of a diffuser is to create this nice, clean, that's why we want it smooth, right? Nice, clean air that is being accelerated in the front and then expanded in the back. And both of those are going to create a downforce. And at our speeds, which are not Formula One speeds, the diffuser reigns supreme as far as the primary source of downforce, but that's at 200 miles an hour. In our speeds, it is significant, but its efficiency is almost perfect because it's not adding any real drag, okay? So you should talk about that. And if you are going to show up to competition and you're going to I had three choices, right? Because there's only, Adrian's got a small team on the manufacturing side. I can't manufacture 10,000 different elements and put them everywhere, right? Some of the teams have a whole team of dozens of, freshmen who just sit there and mold out stuff, right? But at the end of the day, you got a choice. You got three main things to build. And if you can only show up with a front wing and a rear wing, I'm going to ask you why you chose the drag creating elements instead of the not so draggy creating elements. And I remember having a conversation with a student years ago about that. And he was adamant that the car was faster they designed all three. They built all three. They missed their mark on the performance of the diffuser. Their models weren't right. They made some bad assumptions. And he's like, yeah, so all three weren't working well. So I took the diffuser off. And I was like, you just raised the CG, because adding the diffuser is adding mass below the CG. So why does the diffuser work? You get downforce, and if it's designed well, you get quite a bit. It adds little to no drag, and it lowers the CG. 3 for 3. So if I'm standing there at the vehicle and I see just a rear wing and just a front wing and no diffuser, I got a lot of questions. And you better have a lot of data proving to me that the net effect of removing a diffuser is positive. And there's going to need to be a lot of data to prove it. Does that make sense? So just you know, something to ponder as you guys go back and talk to each other, but also something to prepare for if you are going to talk about designing all 3 elements and showing up with, say, 2. Sometimes we see teams running out of time on the build side. We see it all the time, right? And you guys seem to like you've got a great timeline, and I hope you hit it, but stuff happens, right? So we'll see. But as you make a decision, if you can't show up with 3 elements, make a very, very good engineering decision on which ones you bring and which ones you install in the car, which ones you manufacture, et cetera. And that conversation all is about what's the mass, what's the downforce, what's the drag penalty, and ultimately where does the mass go on the vehicle compared to the CG. So there's a story in there, and there's a good story that you guys can tell. Boop, 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 boop. Yeah, I think those are the big, I mean, those are big ones, right? Conversation around CG location and CP and their relative sort of locations. The CP is going to migrate as a function of velocity. Go to slide 17. That is the coolest slide. Do not get rid of this slide. This is so cool. I have not seen this before. Okay, I haven't seen this sort of GG plot, histogram, and this comparison of width and well arrow. That is a very, very cool plot. Okay. The only problem was it was really hard for me to read. I had to read the small text under select results. Green was FE9 data. And then I had to figure out, oh, that's without arrow because it's got less G's. And then, right. And then purple was something else, FE12. Just take that box out of there, delete it out of the picture, put an arrow to the green, and in green text, write without arrow, put an arrow to the purple, and in purple text, say with arrow. That's all you need to do. And then talk through the fact that we have predicted that Aero is going to help our vehicle in almost all forms of acceleration. Maybe it's moot there at your forward acceleration. That just means it's not adding too much drag. You know, it's pretty much on top of the green. What we don't want to see is we don't see the purple in lower longitudinal acceleration, right? If the purple at the middle and the top is below the green, that means we're slowing it down due to drag. Does that make sense? Anything above that's just mechanical grip. So this is basically showing me that no matter where you are on track, no matter what your vehicle's doing, you are increasing its ability to withstand G forces as a result of down, So cool stuff. I think it's a cool graph. I haven't seen it before, so don't get rid of it. All right, we're just 5 minutes over, but does that help out, guys?
Yes.
No, yeah, definitely. That's
Yeah,
amazing
definitely.
advice.
Cool.
Yep.
Awesome stuff. Well, I think you guys are off to a great start, and I'm super excited to see you guys kind of refine the story a little bit, reanalyze sort of CP location and its role. Gets do some fundamental free-body diagram stuff. Recognize the source of error in your CFD, right? I mean, all CFD has error in it, no matter how complex the model is, and just be blatantly like transparent about it. Like all models are wrong, some are useful is what we say, right? And even with a gigantic, arrow map of yaw sensitivity in 3D, which is kind of the dream. At the end of the day, like very few teams have the knowledge, the hardware, and the resources to execute that. So just recognizing that you're doing sims, you're doing predictions, and whenever you're doing performance, right, predicted performance, the keyword is predicted here. Unless you have hard test data, make sure that some of your, you're not implying that this is the performance. It's not. This is the predicted performance with the simulation, which is why it's important that before you start showing simulation results, you have one slide that explains the simulation and tries to prove its credibility as a tool. Because if you can't prove the credibility and understand the accuracy and the error in the simulation tool, everything after that is like, here's my buddy Joe, and Joe's opinion is this. It's like, all right, well, hang on tight, So just so build that. And if you guys have any questions about your sims and how they're set up and stuff, you can shoot me an email. That's probably the best way to have me give some feedback. You know, if you want to say, hey, this is how I set it up. This is my turbulence model, for example. That's what I do pretty much every day. So I can respond to that email pretty quickly, pretty easily, and give you guys some guidance if it helps.
Yeah, I just wanted to ask if you can give us like some pointers on like what we could do to like help prove like the Sims credibility.
Yep.
Like
The mesh. So you're going to want to talk about the mesh a little bit, and you're going to want to talk about the turbulence model, which should be K omega SST. That is the generally accepted industry best practice for what we call a bluff body in ground effect, which is the fancy way of saying a race car. And there is a certain term or parameter that we are very interested in with respect to the accuracy of the turbulence model. So the turbulence model is the part of the math, right, that is predicting how turbulent it is. And how turbulent the air is going to impact whether the air is going to separate from the low pressure side. Because if your angle of attack on the third element is too high, and you have not accurately modeled the airflow in the low pressure side, so on the low side, on the bottom side of your air elements, you're going to separate in real life even though your CFD doesn't show separation. So when I see something like the third element at a 55-degree angle of attack, which is what you showed me, man, if your model's wrong, A, you're not getting the downforce you think you are, and B, you got less downforce than you think and you have more drag than you think you do. And so that's the one area that is the most critical in CFD for these types of cars is the second, third, fourth element in a multi-element. It's such a high angle of attack. You're at such a high risk of separating the air. And as soon as you separate the air, that element is dead to us, doesn't do anything, right? And your downforce and drag numbers are off, potentially by a lot. If you were to ask me, hey, Jim, can you do an analysis on this rear wing? This is the information I'm going to tell you. Here's the contribution of downforce from elements 1, 2, 3, and 4. That's the level of detail that we can get from CFD. The total downforce, 30 pounds at 25 miles an hour. Of those 30 pounds, I'm getting this much from the front main wing, this one from the second element, and this one from the third, and this one from the fourth. You know what I mean?
Yeah.
And then you can start to understand like, my CFD predicts that 95% of my downforce comes from that third element at a 55-degree angle of attack. If my model of that element is wrong, then my whole CFD model is wrong by 95%. Ouch. You know what I mean?
Mm-hmm.
And how we understand if you are accurately predicting potential separation is using the right turbulence model. K omega is the right one. K omega SST is a version of it that's a little bit more efficient. So do the homework on that. And then the K omega SST, the turbulence model and the mesh size have to be on the same page. If your mesh size is too coarse, all bets are off. And the parameter or the number that we look at is called Y plus. Have you heard that term before?
No, I don't recognize it.
In STAR, when you're post-processing and you're like, show me a plot of velocity, show me a plot of pressure, right? Which are the two most common ones that you're going to be looking at. Plot Y plus, or what's called wall Y plus, and research what Y plus is. Y plus is a dimensionless parameter. Excuse me. It correlates the turbulence model that you've chosen to the mesh size at the wall. Because we all know what the velocity is at the wall, 0. The first particle of air is stuck to the side of the vehicle with shear forces. That's what viscosity is. Viscosity is shear, right? It's how the fluid shears over itself. So because air has a viscosity, it's not in a vacuum like in space, we have the first particle of air is stuck to the wall. The second particle of air is not. The 1 millionth particle of air is at 25 miles an hour because that's the speed that our car is moving at. But what's the you know, as you get closer to the wall between 25 miles an hour and 0, what does that profile look like? That's number one, that's the boundary layer. So as you're explaining your understanding of CFD and understanding of fluids and understanding of how air moves around a car or car moves in air, you got to talk about the boundary layer, which is how much and how quickly the air slows down as it gets to the wall or speeds up as it gets away from the wall. And in CFD, because it's just a big dumb piece of software that we've broken this complex geometry into little boxes, right? Little polygons or little hexahedra or tetrahedra, whatever, is every single one of those nodes or cells has a velocity associated to it. And I need to make sure that the mesh up against that wall has enough layers in it to accurately model the boundary layer. That's the key. If you can get your mesh size down, which means, and this is where you make sure you write this down, for K omega, SST or K omega, okay, you want a Y plus value between 1 and 10. If you've never checked your Y plus model, you're probably going to turn on Y plus. It's going to map color onto the body of the vehicle. It's going to map this color plot right onto the wall. And you're going to look at that legend and it's going to be like, cool, I'm at like 0.1 in the blue, but your red's going to be like 1,000. And you're going to be like, shit, pardon my French, shoot. Because what that means is your turbulence model in the area where the mesh is too tall, i.e. 1,000 instead of 10, that second cell, because the first cell is 0 velocity, the second cell, the turbulence model injects a number. It guesses, it's literally guessing, right? Like we you know, it's literally, okay, the first cell is 0 velocity because it's up against the wall. The second cell is 3, I don't know. But if your Y plus, meaning your cell height is too tall, then it's injecting the wrong velocity at the wrong point. Does that make sense?
Mm-hmm. Yeah.
So if your computer, okay, and let's say you look at this and you're like, oh, my Y plus is like up in the thousands. Holy crap, my model's all wrong, which is true. It's all wrong. your downforce and your drag is going to be wrong. Then what you want to try to do is say, okay, well, if I have to minimize, and you only have to minimize the first layer. So the meshing in star, you can literally define the height of the first layer. It's usually not the default option on how you define your mesh. There's other ways to it, but usually you just define the first layer. And then you want to put a second, third, fourth, fifth layer on it. But if your computer's not big enough, okay, if it's not, then you're going to want to use a different turbulence model. There's a different turbulence model called K epsilon. K epsilon.
That's what we use.
That's what you use? Okay.
Yeah.
And that's okay. But your Y plus should be around 300. So if you've got a coarse mesh because your computer's not powerful enough, you really need to use a K epsilon. But in industry, we know that the K epsilon is wrong.
What was the range again? 300?
Yeah, so I would say for K epsilon, you'd probably want to be in the 100 to 300 range. I'm going to send you guys a picture. This is all defined by what we call the law of the wall. So I'm going to send you a link. Where's the chat? Yeah, wiki, the law of the wall. So the law of the wall is, you look at that picture, basically shows you what Y plus model, or what Y plus value associates to a certain terminus model. So jump into that, but ultimately as you dig closer and closer to the wall, i.e. a Y plus goes down, then you're more accurately predicting shear forces in the boundary layer. And so your turbulence model should reflect that. So the most accurate drag and downforce that we do with a I'll say out of the box model like K omega is K omega. We call it two equation, K and omega. But if you can't afford, meaning your computer's not powerful enough to get really small mesh up against the wall, then you have to use K epsilon. Because even though K epsilon is inaccurate, it's not as inaccurate as using a K omega with a mesh that doesn't match, if that makes any sense. Right? Mm-hmm. So your hardware is driving your mesh size, because you can't throw in a billion elements, if your laptop can't handle it. So your hardware kind of drives the mesh size, and then you pick your turbulence model to match. Mm-hmm. Does that make sense? Mm-hmm. So one slide talking about here's my grid, here's my Y plus value, and here is my turbulence model and why I chose it, is going to basically explain how much or how little error you have. It's going to prove the credibility, right? And also at the same time, prove to the audience, like a design judge, that that the model's wrong, but you can try to control and minimize the error as much as possible. Does that make sense?
Yep.
Cool.
All right. Yeah. Don't want to take too much of your time, but
yeah, it's
thank you
lunchtime over
again.
here, so I don't have a call to jump on, but this is key stuff that I wish I learned when I was in school. I had to learn this the hard way.
Yeah. No, this
Yeah,
really
not the
puts
fun
us
way.
this really puts us on a good track.
Yeah.
For sure. I mean, if this is your first year doing Aero and we're having conversations about Y plus and CFD modeling, you're ahead of the curve, because usually teams are out there, doing Aero, and they don't have any modeling on the radar, and they're doing trial and error. And man, is that painful. Man, it takes a long time. Sounds like, I think you guys have a great, you're pointed in the right direction. You're beginning your sort of path in simulation modeling, which is so important in Aero because it's just so hard and complex and expensive to go to a wind tunnel or whatever. And it sounds like you've got a really good direction on the manufacturing side of things. So it's going to be light structure. So I'm super excited for you guys.
Yeah. Well, yeah, we'll try and keep you updated with that, and hopefully see you at Comp.
Sounds good.
Yeah.
Yeah. I mean, you know me, I'll be there. I'll be tech inspection on Wednesday, design judging on Thursday, and design judge feedback on Friday, and then watching some racing on Saturday. So that's usually my schedule.
Awesome.
So,
Yeah.
awesome.
Yeah, if you ever want to come back to Davis to give another panel, we'd love to have you. But
Of
if not,
course.
yeah, just reach out to Heather.
Yeah.
Mhm.
And I try not to do schools back-to-back years. I mean, I'll go anywhere, anytime. It's really up to SAE. I've already got two more. I've got two schools I'm doing this summer, and there's probably going to be two more that pop up in the fall. Since we're talking right now, you're getting a lot of key information that would probably come up in that lecture. We've got an open line of communication on email. And let's see see where this puts you guys for next year. And then if we want to do a lecture after that, let's go for it.
Yeah. Yeah. We'll keep in touch with you with that.
Sounds good.
Awesome. Thank you so much again, Jim.
Yeah.
Yeah,
Thank
it was
you so
amazing.
Absolutely, guys. Thanks
you.
for reaching out. Good luck. And yeah, we'll stay in touch.
Awesome.
All right, bye.
I gotta go work.
Oh my goodness. He was talking about a lot of things that we just forgot to put in.
Yeah.
Yeah,
Like the center of gravity, right?
Yeah.
I mean, yeah, that and also like what's it? Like a lot of the CFD stuff. Like I had answers for some of them, but I guess I should have put it on the slide.
Yeah. I mean, at least we know that, or at least we have those answers, and it's not like we don't know.
Yeah.
I think it's just preparing the slides more.
How do we stop this recording?